I'm Talia Brendel.
Hi, I'm Tyler Thompson.
Hi, I'm Shannon Sire.
And I'm Michael Bruce, and we are the team working on the Open Energy Dashboard Time Varying Conversions update on the server side. Let's get started. We were advised by Stephen Huss Letterman, overseer of the OED project.
OED, short for Open Energy Dashboard, is a free open source web application that helps organizations visualize their energy and resource data. Version 3.00 will introduce time varying conversions, for example, tracking costs that change over time. Preparing for this new version required optimizing the existing database SQL logic to maintain performance standards and adding backend components to support the updated UI the front-end team was building. One of the major focus areas was the database and API developed in collaboration with the front-end team. The PostgreSQL schema and SQL were updated to support day and week time varying conversions. Over 25 new admin-only REST API routes were created, and a Postman OED collection was built to keep endpoint testing organized. Each route includes its purpose, query parameters, and example request and response. This collection and documentation have been handed over to OED so the team can continue using it and adding new routes in the future. For example, if you wanted to see an example of adding a day pattern, you would go to the left here, go into the folder. For day patterns, select Add Day, and here you can see the endpoint URL, the purpose, any authorization needed, query parameters, and an example request and example response. This collection and documentation have been handed over to OED so the team can continue using it and adding new routes in the future. Key challenges included ensuring continuous time coverage without overlaps, resolving legacy code conflicts, and addressing differences in how PostgreSQL and JavaScript handle infinity values.
We began by building on the previous group's implementation. Rather than embedding the conversion logic directly within the graphing function, we refractored it into a materialized view. This allowed hourly conversions to be pre-computed and stored for improved performance. Additionally, a daily materialized view was created to store daily aggregates of the converted hourly data. Notably, the daily view does not apply conversions directly. Instead, it aggregates the already converted hourly values. The graphing functions were updated to retrieve converted readings from these views, eliminating the need to apply conversions on the fly during each query. After building the initial views, we tested, timed, and documented multiple index configurations to see which ones would give the fastest query times. From our analysis, we selected a composite index that works for both hourly and daily and is defined on the meter ID, graphic unit ID, and lower bounds of the time interval. This index provided the most consistent performance improvement across the relevant queries. During testing, we found that our hourly view only worked when a single conversion was being applied to a reading, or conversions of equal length. If the conversions had unequal lengths or if they partially overlapped the reading, the results became inaccurate. This implementation was also dependent on the old view that stored the unconverted hourly readings. To solve this, we created a new hourly view, which uses a common table expression to store the unconverted hourly readings and uses the intersection between the conversion and a reading to apply a weighted average conversion. This solved the aforementioned issues, but further testing revealed that there was a loss of precision due to applying conversions to an average hourly rate. It was also impossible to derive accurate minimum and maximum ranks without referencing the raw data. To address this loss of precision, we created an additional materialized view that applied conversions directly to the raw readings and stored the results. Then we developed a new hourly view, which aggregates converted raw readings into hourly data, similar to how our daily view functions. This approach eliminates the need to apply conversions directly at the hourly level, since the raw readings are already converted and the hourly readings became an aggregate of those converted values. However, after observing several test cases, it became clear that this method also had its limitations, albeit somewhat of an inverse of the previous approach. When raw readings span across multiple hourly partitions, the hourly aggregates no longer reflect only the conversions that apply within the specific hour. Instead, they also include the effects of conversions applied to the portions of the raw readings that lie outside the hour being analyzed.
Considering the potential loss in performance by adding time-varying conversions, we tangentially investigated the viability of a Postgres extension called TimescaleDB. It would theoretically provide higher quality indexing for time series data and potentially allow for partial rebuilds of materialized views, which could improve performance. Due to a lack of viable Postgres Docker images with Timescale installed, we also had to rebuild the dashboard on top of an upgraded version of Postgres. While we made progress towards incorporating the time series features, there was still significant logic changes that needed to be redone on top of Timescale's hypertables. Even after those changes are added, there is still more testing to prove that the time savings are worth the added overhead of Timescale. We left documentation for the next team that will pick this up and can fully realize TimescaleDB and Postgres 17 as an option for OED in the future.
Testing. Testing occurred over three areas: database and API time varying conversions, testing was done on the admin UI routes on the back end. Materialized view, testing focused on performance and accuracy. And timescale DB, testing focused on software validation. Testing methods, admin UI routes. Additional testing for routes was done using the provided Postman collection. The collection significantly reduced Postman setup and testing execute time as all Postman requests are already created. Materialized views. Automated testing reduced the number of steps by a factor of 8 in some areas for a single test with parameters. In addition, a user could run 10 tests with different parameters through a single test suite request, which would have required multiple repeated steps before. Currently, timescale DB. Currently, testing consists of OED tests for continuous integration and software validation and will be expanded to include testing for materialized view and admin UI routes. Here we have 2 examples of testing for performance. On the left, we have multiple parameter testing, and on the lower right, we have single parameter testing, and we have the test suite used to create these. Here we have testing for accuracy. On the left, we have a test case for meter roll readings unit, and on the lower right, we have a test case for meter hours readings unit. Thank you. As a team, working together on the OED project was a tremendously rewarding experience, and we were all very grateful to have had the opportunity to contribute to OED. Some of us will continue to work on OED in the near future, while others, having left their mark on OED, will move on, taking the benefits of the OED experience with them. We all would like to thank Steve Huss-Letterman from OED, Kayla Rolacek, Professor Robertson, Dr. Sue, and everyone else from CSUMB for a wonderful conclusion to a most exceptional journey we've had coming through the CSUMB CS online program. All of us are leaving CSUMB better prepared than when we first arrived. With our thanks from Michael Bruce, Talia Frendel, Shannon Sire, and Tyler Thompson.